All right, so here we have a lovely picture with a pin thrown in for scale, which is very important, of a hunk of fat and a hunk of muscle. That's all we know. We won't ask any questions about where these things come from. But the important thing to consider here is that they are trying to show us that, hey, if I give you the exact same mass of two different substances, 2 kilograms of muscle, 2 kilograms of fat, guess what? The resulting space or volume that they occupy will be very different. So what do we clearly see here? When it comes to fat, 2 kilograms of fat will take up a much greater amount of space than 2 kilograms of muscle. So it takes a lot more. If I had a large amount of muscle, just to equal the fat, obviously, you know what I'd have to do? I would be bumping up my mass considerably. To get the same amount of volume of muscle as you have fat, you're going to be increasing mass substantially. If you keep it equal, if you keep all this equal, which we're doing here, guess what? You are clearly showing that muscle is much more dense than fat because 2 kilograms occupies a much smaller volume of muscle than 2 kilograms of fat. It will occupy a much larger volume. So basically, this all comes down to a concept of compactness. When you think about density, yeah, we're talking mass volume units, but just think dense things are more compact than less dense objects. All you're doing is you are taking a larger amount of mass and you're putting it in a smaller space and you get compactness. So when you're comparing two objects, the one that's more dense has more mass per unit volume that you're dealing with. So think of, if you've got these particles flying around here and they're loose, non-compact, occupying a large area, versus you have particles that are crunched together, put in a smaller space, occupied or ordered, arranged. And you compare them, this is going to be more dense than this sample. So when it comes to compactness, compact things typically are more dense because you have more stuff crammed in the same amount of space. So being able to get things compact, you can have the same mass and put it in a smaller space, but then you're increasing density because you're comparing mass to volume. So when you're looking at compactness, that is a good general way of thinking about density. Things that are same substance but more compact are going to be more dense. So it's go time here. So this is where you take a deep breath, you don't freak out, and you realize, yes, you are looking at a equation. For some of you, it might be your first chemistry equation, and that's cool. D equals m over v. And here you have units, mass, kilograms, grams, milliliters, or cubic centimeters. Some people get anxiety attacks over an exponent here. Oh goodness, here's 2 units, grams per mil. So this is a lot of stuff that could possibly cause some anxiety. Let's not do that. Let's look at the big picture of what I am seeing here, of this comparison. We just got done discussing that, hey, when it comes to muscle, you've got a lot more mass packed in a small space than fat. If you have the same amount of mass, you've got a much larger volume of fat, smaller volume of muscle. But we said that's more dense. You've got more space, less volume. You have more mass, less volume. So all we're doing is we're comparing the relationship of mass to volume of any given sample of anything, and that will be its density. So how do we compare? Well, we divide. I want to know how much mass do I have in a given space, so that will be mass divided by volume. That's how we compare those two in a relationship. How much mass in a space? M over V. That's all we're doing. So if I give you the mass of a substance and I give you the amount of space it's taking up, guess what? I can find, yeah, my density. So when we solve for density, that's all we're looking for. I want to know how much stuff do I have? What is my mass? I want to know what space is it taking up? That's my volume. And then I want to just do the simple math. Mass divided by volume, and I get the density of that substance. So then the rest of it has to do with playing with units. So when it comes to mass, easy enough. For mass, we're dealing with grams in these samples we're going to be showing you. It could be kilograms, decigrams, centigrams, but grams is our mass unit. Volume, on the other hand, is a little more complicated because volume of liquids is measured in liters, typically. So if we're doing solids, and what we call a regular solid, if it's something that you can actually measure dimensions of, for instance, length times width times height, we will get a cubic unit. So here we have a liquid volume unit for milliliters, but then we have this cubic centimeter. Nothing to fear, okay? Because all I've done here is I have taken a length in centimeters, multiplied it by width in centimeters, multiplied that by the height in centimeters. So just like numbers, if I had 2 times 2, that's the same thing as 2 squared, right? 2 times 2 times 2 is 2 cubed. So anytime I take something and I actually multiply it by itself, it's going to be squared, multiply it by itself 3 times, cubed. Well, guess what we're doing? I'm multiplying a unit by itself 3 times. That's why you always want to have the pen. And when I multiply the unit by itself 3 times, same rule, I just get cubic centimeters. So all this means is I have multiplied length times width times height, dimensions, to get the volume of a solid, and the resulting unit is going to be a cubic centimeter. For a liquid, I could pour it into a graduated cylinder and I would measure it in milliliters. So both volume, just different units to express them. And this is what's so cool that you will love. And it says fun facts to memorize. Usually we give you these facts, but in this case, 1 milliliter turns out, yeehaw, to equal 1 cubic centimeter, or cc. So it is a one-to-one relationship. So even I could express the volume of a solid in milliliters, and it's not that I'm wrong. You don't really think of solids having volumes in milliliters. Typically, that's a liquid measurement. But if it was 4.8 milliliters, that's the same thing as 4.8 cubic centimeters. It is a one-to-one relationship. So this is a great time to see. Whenever we calculate in mils, I can instantly turn it into cubic centimeters. They're the same thing. Likewise, if I have a cubic centimeter measurement, I can instantly turn it into milliliters. That comes in handy. We use water displacement to be able to determine the volume of a solid we can't measure evenly with length, width, and height. Lastly here, we will look at this important concept. Moving forward, when we're doing density columns or fun things like that, the density of water is an important standard that we're using, and we set that density. That is 1 gram per milliliter. This unit, grams per milliliter, that's called a derived unit because most everything we've seen so far is a single unit, a number, and a unit. But a derived unit means I had to do a process to get this unit. I had to divide things that didn't cancel because, as we saw with dimensional analysis, units on top cancel units on bottom. Well, what if we have a situation where we have a unit, gram on top, and milliliter on bottom, and they don't match? They can't cancel. They don't cancel each other out. So whatever you're dividing here, the final unit is going to have to stay both of these. So it is going to be grams over mils, or grams per milliliter, as we would say. Well, guess what? What am I doing here? Look at that. All I'm doing is dividing mass by volume. A gram unit mass for milliliter volume unit, I get grams per mil. So this is the density unit, grams per milliliter, for water being a liquid. If it was solid, you could say grams per cubic centimeter. Same thing. Okay? They are equal to each other. So you get the privilege of being able to make them convert instantly. So